Hello, I'm Bill Hearl, President and CEO of Imunomic Therapeutics. Today's presentation is on next-generation vaccines from prevention to cures. I'm going to give you a brief overview on the history of vaccines, a quick walk through current technologies in preventive vaccines, and then a look at our next-generation vaccine for treating cancer. So as we move today from being able to prevent diseases such as COVID-19 to being able to treat cancer, we see a whole new frontier of opportunities in the development of vaccines. So I'd like to start out with this quote from Greta Keenan, which says that it's no secret that vaccines have revolutionized global health. Clearly, it is amongst the most life-saving innovations in the history of medicine. And so things such as smallpox and polio have been eliminated, child mortality rates have greatly decreased, and it's prevented lifelong disabilities from diseases such as polio. So, and we look at the history of vaccines, actually, it dates back centuries. Very early on, a smallpox vaccine was created that was actually just ground up pox scabs. It was used as an inhalant and then as a kind of a tattoo approach. Then we went to more well-defined smallpox vaccines until Pasteur created the first vaccine that used live attenuated bacteria for chicken cholera, and then followed that up with the first vaccine for a virus, which was for rabies. As we went through, as technology advanced, we saw new things evolve, such as the inactivating of polio vaccine, which was key, and then any number of vaccines that particularly affected childhood diseases, such as measles, and then also hepatitis, influenza, tetanus. And then more recently, we've seen things such as the pneumonia vaccine, meningitis, and HPV. And of course, we're all quite well aware of the advances that we've seen with COVID-19 and the new generation of messenger RNA vaccines. So this is a long history and a successful history of treating vaccines. We can look at how this has impacted the number of active disease cases as more vaccines have come online. So just in the United States, if we looked at annual cases and in around the early 1900s, you saw many cases of any number of vaccines. And we jump ahead to current times and we see that diseases such as polio and smallpox have been eradicated, and virtually eradicated are some things such as measles, mumps, diphtheria, rubella, pertussis, all things that are well addressed by current vaccines. So there is hard, tangible evidence of the positive effect of vaccines on human health. Now, one thing that we've seen, and this can be illustrated over time, is that the kinds of vaccines that have been used have changed as well, starting with what was the early live attenuated vaccines and then inactivated vaccines for bacteria and for viruses that were quite effective. And then they evolved into vaccine parts and then peptides. And now more recently, we've seen things such as virus-like particles. And of course, the DNA and RNA formulations, you're going to see more recombinant subunits that also form as part of virus-like particles. And of course, you also have recombinant viral vectors, such as the adenovirus COVID-19 vaccine. So it's important to understand how these vaccines work and what happens and how this actually results in immune activation. So if you have an injection, a shot that delivers attenuated virus or killed virus or even protein antigens, what happens is at the cell surface of immune cells, such as your white blood cells that are attracted to the scene, they pick up these proteins and virus particles and they process them into a vesicle, the early endosome, which which merges in with components that are coming through the new protein manufacture pathway that results in the presence of MHC2 molecules that form a lysosome, where these peptides are digested into small parts, and these peptides load onto the surface of the MHC2, and they find their way to the surface of the cell, where they activate through helper T cells. So this is an extraordinarily effective method for activating the immune cells, and the MHC2 pathway is only found on immune cells. So, for example, muscle cells do not express MHC2 in any significant way. And this approach is really ideal, particularly for diseases that are easily identified by the immune system. So the reason that smallpox and polio created such effective vaccines was for that very reason. You saw that there was a potent immune response historically against those viruses. So the only liabilities and problems with this design is that you're limited to being able to produce it against viruses and bacteria that you can grow. And then you have questions of stability and scalability and logistical issues such as whether the vaccine needs to be frozen or not. That all limit the utility of certain vaccines. So that's the way that a conventional vaccine works. More recently, we've seen, of course, DNA or messenger RNA coding as antigens. And this is a very different approach. In this case, the nucleic acid actually arrives inside the cell, and it uses the host machinery to synthesize the antigen. And so this endogenously synthesized protein can then be processed through the proteasome into smaller peptides, and it goes through what's known as the TAP pathway and has access to the MHC class 1. And so MHC class 1 is present on all cells and is transported to the surface of cells, whether they're immune cells or muscle cells or other somatic cells. And in this way, they interact generally with CD8 cells. So the cytotoxic T cells are present and interact with the T cell receptor and the MHC1 molecule. So this is a pathway that's particularly useful for viruses and other agents that reside intracellularly. We would expect that this to be an effective pathway for things such as HIV, HPV, hepatitis. But obviously, we see, because of the potent nature of the response to COVID-19, you can also use this in the nanoparticle formulation to create a broader and more robust immune response. So the impact that we see on humans, on the human population of this kind of vaccine, is illustrated in the next slide, where in this case you have the unvaccinated in the red in cases, hospitalizations, and deaths, all as a function of population size. And you see the various waves, the initial COVID range, which was variant alpha, and then the more virulent Delta virus variant, which had responses that were much more infectious and had a greater impact. So you would see some breakthrough even in the vaccinated individuals. Hospitalizations, however, were down, and deaths were dramatically decreased in the vaccinated population. So as a prophylactic vaccine, we can see even now, when faced with a new infectious agent, being able to rapidly respond and create a vaccine can save a large segment of the population from dire consequences by deploying these kinds of vaccines. So as we look over time, what we've seen is that the initial vaccines had targeted highly infectious diseases, and they used killed or attenuated biologics to achieve that. More recently, as we went through the next generation of vaccines, you went after more challenging targets and were able to use virus particles or bacterial proteins as components to prevent disease. So it was a different way of approaching activating the immune system, but with the same basic intent and result. The third generation of vaccines now utilizing messenger RNA or DNA to use the host to synthesize the target proteins, such as the spike protein of COVID-19. And the next generation that's coming, and the exciting application of vaccines, is being used in a cell therapy and with the messenger RNA or DNA vaccine to treat diseases such as cancer, with the ultimate goal being a cure and a therapeutic through immune system activation. And so we're going to take a couple of minutes and discuss that. So I'd like to talk to you a little bit about our initiative in applying vaccines for cancer therapy and using our Unite platform to apply for cancer vaccines and offer new approaches to treating oncological disease. So our Unite platform utilizes the gene LAMP1 to focus delivery of the antigen into the MHC2 pathway. This is a very unique approach, and what we are able to achieve with this is actually very efficient delivery of antigen into the lysosome compartment, where it's free to interact with the MHC2 molecule, load directly into the MHC2 binding cleft, and be presented on the outside of the cell. The result is that you're going to get a very potent immune response. So how does this compare when we look at conventional vaccines, which, as you may recall, comes in from the outside of the cell, processes into the lysosome, meets up with the MHC2 complex, and then interacts with helper T cells, and also with nucleic acid vaccines, where the antigen is synthesized intracellularly, goes through the TAP pathway, and primarily interacts with the immune system through MHC1. With the Unite-based LAMP vaccines, now the antigen is actually primarily synthesized directly into the Golgi complex and is able to find its way directly to and co-migrate with MHC2. So these proteins, as they pinch off and form the lysosome, the antigen is already present, and you get direct activation of MHC2, so you get the best of the conventional vaccine. But there's also a certain amount of natural leakage into the TAP pathway, so you get MHC1 presentation as well. So in the formation of the Unite LAMP vaccines, you get the best of MHC1 and MHC2 in activating the immune system. So as we look at this and compare that concept, you're looking at limited activation through conventional nucleic acid vaccines, and in particular, I think where we see a limitation is in the ability to create a very potent memory response. And when you think about a vaccine, memory is absolutely key to having an effective vaccine. I think we can all agree that we would not want to be getting a tetanus shot every 6 months, and we don't want to really have to be getting COVID or influenza shots every year if we didn't have to. So the idea of creating long-lived memory is really important, and that's a key feature of the LAMP Unite mediated immunization. So you get this complete immune response that involves all aspects of the immune system: helper T cells, cytotoxic T cells, antibodies, and immune memory. This also allows us to incorporate what we believe is perhaps one of the most potent ways of activating the immune system, and that is loading dendritic cells, which are very active in educating the immune system as to foreign antigens, as cells that go around and essentially scoop up the infecting agents or allergens or any foreign proteins, processing it and presenting it to helper T cells. We can load these cells directly with the messenger RNA vaccine and use that as a direct conduit to the immune system. There are other possibilities that are out there for development, which we don't have time to discuss today, such as directly creating therapeutic antibodies, using self-amplifying RNA for immuno-oncology, and of course continuing work on plasmid DNA for infectious disease. And there's some very interesting applications in skin cancer, and in particular in Merkel cell carcinoma, where this particular approach could be a very promising way of preventing recurrence. So as we look at ways of dealing with infiltrating the tumor and responding, this illustration explains in an overall view how this works. So a LAMP-mediated vaccine gets into the cell, the protein is processed, and it either finds its way into the lysosome, where it's free to bind with MHC2 and get to the surface of the cell and activate helper T cells, or it has the ability to process through the proteasome, enter MHC1, and activate cytotoxic T cells. When you have the helper T cells are able to enhance activation and expand the development of the cytotoxic T cells, and they're also key for memory development. A certain amount of these helper T cells also will find their way into the tumor environment, but the largest number of activated cells in the tumor are going to be your cytotoxic T cells, and they are very strong expressors of interferon gamma, which is a potent cytokine that all leads to tumor cell death. So as an example and a practical application of this, we've been working in brain cancer and in particular glioblastoma. This is a very negative disease for the patient. It has a very high mortality rate. The 2-year survival rate is poor at less than 40%. The number of patients that are seen worldwide is approximately 50,000 patients per year with newly diagnosed cases, 10,000 in the United States alone. And there has not been a new approved treatment for glioblastoma in over 20 years. So our approach is a therapeutic which we have tentatively called ITI-1000, and it's a pulsed dendritic cell that's loaded with a vaccine, a messenger RNA vaccine that codes for a CMV protein, PP65. And so it's given with an adjuvant of tetanus toxin, and that is there to help attract cells to the injection site. And so it offers a targeted approach to brain cancer. And the early data, as you'll see, is really quite exciting in terms of providing for both overall survival and long-term survival in a large number of patients. So we have an ongoing study, and we'll briefly touch on that. So in this data from the phase 1 study, the median survival of the patients that received the cell therapeutic vaccine had overall survival rates of around 50% for over 40 months. And so these patients had very long-term survival, actually out a number of years. And so there was a second arm of this study which used GM-CSF as an adjuvant, also had substantial survival benefit, around 40 months overall survival, and long-term survival benefit in these patients lasting several years. So this is a remarkable result and shows the power of how a cancer vaccine can actually impact the survival curve and provide survival benefit to brain cancer patients who under other circumstances would be in extreme jeopardy. So the study that we have going on now is a phase 2 study. It's a blinded study that has 2 test arms with different formulations of the vaccine and a placebo comparator, which is unpulsed blood lymphocytes. And so in this study, what you see is that they're getting a number of doses, up to 10 doses, over a period of several months, and until they observe progression. So this study is making very good progress. And at the moment, the first patient was actually dosed in 2016. We now have over 120 enrollees and approximately 100 patients under study at the moment. We expect to have 100 patients close to 24-month survival data sometime early next year. And we've actually added a new arm to the study called Renew, which would enable us to treat subjects that did not meet the criteria for attack 2, but otherwise would still be excellent candidates for treatment using this type of vaccine. So we see two main areas where vaccines are going to continue to grow and be important in human health. You know from history that vaccines have had a dramatic impact on the role of human health in bringing many deadly diseases under control. We know that vaccines continue to be an effective tool in fighting infectious diseases, and that there are disease targets such as HIV, which are still in need of a good preventative vaccine. We also know that cancer vaccines are a new class of immune activators, and what you're trying to do in this particular case then is create a potent immune response against active disease, so that vaccines now would also be viewed as therapeutic. And we believe that the dendritic cell therapy is an excellent example of how these types of cancer vaccines can induce the immune system to fight ongoing disease. And although we didn't have time for this today, we would also have been able to show you data where cancer vaccines were effective against multiple indications using human telomerase as the antigen and multiple antigens. So not only the CMV antigen PP65, but also such as this mentioned human telomerase and certain melanoma antigens such as MAGE3 and others in that family. So I think on that particular note, I'm going to conclude my study and presentation. If you have any questions, please feel free to contact me at my email, or you can text me or call me by phone. Thank you very much. I appreciate the opportunity to speak with you today.